Hi, let's continue with phase space portraits. So let's just recall some of the points. Right. The first step in plotting the phase space portrait is to plot v of x as a function of x or u of x as a function of x. Right. That's a potential energy curve. Right. Now we have to find the zeros. So in order to plot v of x with x, all right, v of x versus x, there are a few steps that we can take. All right, we can first find the zeros of the potential energy curve. We'll see on which points the potential energy becomes zero. Okay, we'll find the extrema of v of x. Right, we have to find the extrema, the points in the x-axis where it's maxima and minima. We need to find which extrema are maxima and which are minima. All right, so in order to find the extrema, we said that we have to take the first derivative, equate it to zero. All right, solving that equation will give you the points where the potential energy curve is maxima or minima. Right, and we have to determine whether these are actually maxima or minima. Okay, for that, we find the second derivative at each of these points. Right, and using these details, we can just plot a qualitative curve for v of x. All right, the next step after plotting v of x is to draw energy lines. All right, we draw different lines corresponding to different energies, different possible energies of the particle. Right, and you have to remember that the regions were E less than v. Right, so if you have this x-axis like this and some potential like that, all right, and we have got this energy line E. Right, see, if you look at this point, E, this height is E, okay, and this height is v. So at this point in x, the height of E is less than height of v. Right, so E is less than v, and this region is classically forbidden. So if you look at it within these regions, all right, in this case within this region is classically forbidden. All right, this is actually a segment along the x-axis. All right, that segment is completely forbidden for that particular particle of energy E. Right, so these regions are classically forbidden where E is less than v. Right, and we have to remember that when E is equal to P, so E is equal to V, then P is equal to 0, the momentum is equal to 0. And again, we said that we have to put arrow marks on the curves. All right, if P is positive, the arrow should be towards the positive x direction, and if P is negative, it should be towards the negative x direction. Right. Also, we said that the phase space trajectories do not intersect for autonomous systems. All right, that's a statement for the conservation of energy or reversibility or determinism. All right, all these things we have discussed. We also discussed the problem for a simple harmonic motion. We already know the plot for half kx square, but you could try to plot this using the steps that we highlighted. All right, let's go to the next problem. I hope you have tried it. Okay, so we'll go into some detail with this particular example. All right, so the other things, the other problems we'll see that are similar to these things. So we have got v of x equal to minus half kx square. Okay, now you already know it's a parabola like this, right? It's a parabola like this. V of x, the parabola v of x versus x is a parabola like this. We already know that, but let's imagine we don't know this. Let's try to follow the steps that we outlined. Okay. The first step was to find the zeros of the potential energy curve. Right? So we say that v of x equal to 0. So minus half kx square is equal to 0. Now this is 0 for the solution to this is x equal to 0. Okay? So we know that for the potential energy curve, we know that x equal to 0, the potential energy is 0. That's only point where the potential energy is 0. So we got 1 point. Okay, so what do we do to get the other points? We have to find the maxima and minima. All right, so we take the first derivative, which is minus 2kx, and say that this is equal to 0. Right, so you see that x equal to 0 is the only extremum point it has. It's the only extremum point it has. All right, so it could either be a maximum or a minimum at x equal to 0. All right, so the solution to dv by dx equal to 0 is x equal to 0. So at the point where the potential energy is 0, we have also got a maximum or a minimum. Okay, this is also an extremum point. Also, the potential energy is 0 there. Okay, so to find whether it's a maximum or a minimum, what we do is that we take the second derivative. Right, we take the second derivative and see that minus 2k. That's the second derivative at x equal to 0. That's negative. Right, that's because there is no x dependence here. So this is minus 2k. That's negative. Okay, so we said that if the second derivative is negative, then this is the maxima. Okay, if the second derivative is positive, then we have got a minimum, and if the second derivative is negative, we have got a maximum point here. Alright, so this is a point of maximum. So we have got enough details now. Right, so we'll also find what's the value of the potential energy at x equal to 0, at the minimum point. We see that at x equal to 0 already v of x is 0. Okay, so we see that this is a maxima. This is a maximum. This extremum is a maximum, it's not a minimum, which means that this is the maximum value the potential energy can take along the x-axis. Alright, this means that it has to be less than that. So it's easy to plot the parabola now. There are no other extremum points. Right, so you see that the qualitative behavior is something like that. Okay, that was not very difficult. Alright, now that's we have plotted the potential energy curve. This is the first step we have to do. Okay, but before going into plotting, now we have to draw the energy lines and then plot the the phase space portrait. But before going into this, we can see the general behavior of this. We said that the conservation of energy alone determines the phase space trajectories. Right, so let's look at the conservation of energy. You see that p square by 2m minus half k square is equal to E. Okay, so from here you see that p square by 2m minus x square by 2e by k is equal to 1. Right, now this equation stands for a family of hyperbola. Alright, so the plots that we are going to get is actually a family of hyperbola for different values of energy. Alright, but without using this, let's see how we can plot this actually. Okay, alright, so we have got this x-axis and y-axis drawn here. Along the y-axis we have got v of x. Alright, so first thing, as I said, is to plot the potential energy curve. Alright, that we already did. It said it's a parabola like that. Okay, so it's not exact, but it has to be 0 only at this point. All right, so let's be a little bit more careful here. It's something like that. Okay, it has to be smooth. All right, so that's our potential energy curve. Alright, now we have got the potential energy curve. Okay. Now what's the next step? We have to find points of we have to draw energy lines. Alright, so let's imagine that. So since the potential energy is negative, alright, you have to remember that since the potential energy is negative, E can be negative, alright, because E is T plus V. Right, E is equal to T plus V. So if potential energy is negative, we say that the total energy of the particle also can be negative. Okay, so in this case, the total energy can be negative. So let's draw different energy lines. Okay, different energy lines. Energy lines are just straight lines parallel to x. Okay, these correspond to different possible energies of the particle. Right? So let's draw one energy line here. These are supposed to be straight lines. Okay, let's say this is E1. This is the case where E is less than 0. Okay, let's also have one more, E2. Right, we'll also have one energy line here. Assume that there is one energy line here along this thing that corresponds to E equal to 0. Okay, because the height from the x-axis in this curve has the dimensions of energy, so this line corresponds to E equal to 0. Well, let's say E3. This is less than 0, this is less than 0. We could also draw a couple of energy lines corresponding to, let's say, E4 greater than 0, and then we can also have E5 greater than 0. Okay, that's it. Right? We have drawn the potentials. We have drawn different energy lines, okay, which represent different possible energies of the system. Right? So let's see for E1 less than 0. For E1 less than 0. So we know that at this point along the x-axis where we see that at this point, okay, V of x is equal to, or the potential energy is equal to total energy. Right? Along this point, potential energy is equal to. So along here we plot V of x along the y-axis, and for the phase space portrait we plot Px along the y-axis. Alright, so now what we are going to draw corresponds to Px versus x, or P versus x. Alright, okay, now we know that at this point At this point, we just drop a straight line here, and at this point, v of x is equal to E1. V of x equal to E1 at this point, all right? So at this point, we know that the energy, okay, the momentum will be equal to 0. The kinetic energy or the momentum will be equal to 0. So we already know that this is a point where the momentum will be equal to 0. So first we are plotting case for first we are plotting case for E1, which is less than 0. So these are 2 points where the momentum will become equal to 0. Okay, I hope that much is clear. Now this region is classically forbidden. Why is that? Because we see that this height, right, this height is the energy. Okay, that's the energy, whereas at this point, so right, within this curve, at this height is the, for example, right, at the same point, this height is V. So since this is a negative number, you see that E is less than V within this. So this is classically forbidden. Okay, the region inside is classically forbidden. All right, the region inside is classically forbidden. I hope that's clear. Okay, that's it. Okay, because at this point, let's imagine just some random point along the x-axis. At this point, we see that this height is E. E is negative, V is also negative. All right, so let's say E is something like -6 and V is something like -2. All right, we see that -6 is less than -2. Am I right? -6 is less than -2. It's a minus number. It's a negative number. So this means that this region is classically forbidden. Now let's imagine there's a particle coming from plus infinity. It comes from plus infinity, all right? It does not, it sees more and more of the potential energy. So as it approaches x equal to 0, all right? From plus infinity, a particle is approaching x equal to 0 with energy E1, all right? And it sees that the potential energy actually increases. The potential energy actually increases, all right? There is less potential energy here and it keeps on increasing. Right, it keeps on increasing as it approaches x equal to 0. And at one point, it sees that the total energy of the particle, the potential energy becomes as high as the energy of the particle itself. And at that point, the particle stops, the momentum becomes 0 and it turns around. That's hyperbola. That's hyperbola we are talking about. Okay? I'll just give you a rough diagram here. I'm not very good at drawing, but it's like this. It comes from plus infinity. Okay, it comes from plus infinity like that. It sees more and more of the potential energy, and the potential energy becomes 0 at, the difference of potential energy and total energy becomes 0 here, which means that the momentum becomes 0. So the momentum decreases as it sees more of the potential energy and it becomes 0 at this point, and then it turns around, all right? Then it turns around like that. So that's hyperbola for E1 less than 0. So if you look at the arrow marks goes like this, because in this quadrant P is positive, so it's towards a positive x direction. Likewise here. Okay, all right. This may be a little bit exaggerated, but let's see. And now we can also draw for. We can also imagine particle coming from minus infinity. All right, you can also imagine particle coming from minus infinity. This has to be symmetric about this axis. All right, about the p axis, because we saw that the potential energy, Hamiltonian, one point to remember, Hamiltonian is, let's say, p square by 2m plus, what is it, minus half kx square. That's a Hamiltonian. All right, you see that if you put x to minus x, the Hamiltonian does not change, which means that whether it's minus x or plus x, it's symmetric. It's symmetric about the p-axis. Similarly, if you put p to minus p also, Hamiltonian does not change. So the curve above and below the x-axis are also the same. Okay, there is this symmetry. Okay, so this has to be exactly symmetric. I hope to draw it exactly in a similar way. Let's try. Okay. So this was the case of the particle. Okay, this was the case of the particle that comes from plus infinity. Now imagine there's a particle coming from minus infinity. Again, it will see more and more of the potential energy. Okay, again it will see more and more of the potential energy, and then it will become 0 where E is equal to E1 is equal to V. All right, E1 is equal to V at this point, as we said. So momentum becomes 0. So it is turning point and it turns around and goes. Okay, the arrows goes like this. Okay, because here momentum is negative, so it's towards here the momentum is all right, let's what's the momentum along this? It's negative. All right, so wait a moment. here the momentum is positive, so I think I did it in the wrong way. All right, sorry. So I should have drawn it like this. So there's a particle coming from minus infinity. It comes from here, right? It has a positive, so it's traveling towards the positive x direction. So it comes from here actually. All right, it comes from here. It travels along the positive x direction. Let's say it goes somewhat like this. Okay. As I said, it encounters more and more of the potential energy, and its momentum just drops. Okay, this is just a rough diagram. All right, I'll give you a better diagram in the notes. Right. Comes here with energy E1, it comes from minus infinity towards the positive x direction. It reaches here, its momentum becomes 0, so it turns around, goes back to infinity. That's what's happening. Okay, you see how we put the arrow. Alright, so initially I said it wrongly. The particle with coming from minus infinity travels from minus infinity towards the positive x direction. Alright, so we should start from here. Okay, that's for E1. Similarly, for E2, it's also less than 0. We can draw curves for E2. Right? You see that if the particle has energy E2, it can reach up to here along the x-axis. That's E2. So it can reach up to here along the x-axis. All right. The particle with E1 cannot penetrate this region. Right. Momentum becomes 0 here. But the particle with energy E2, all right, it can reach up to here. So it will go back to infinity from here, and it comes from infinity like that. Okay, like that. Similarly, the particle with energy E2 can reach up to here. All right, it can reach a bit nearer to the 0 of x equal to 0, and it goes like that. It's fine. Okay, this is a family of hyperbola. These are a family of hyperbola. I hope this is clear. Right, now let's take the case for E greater than 0. All right, let's take the case for E greater than 0. In this case, it's free. The particle is actually free. Is E greater than 0. So it will come from infinity. Again, it will see more and more of the potential energy. Its momentum will actually, these are all free particles, or these are all free. The particles are all free here. But in this case, you will see that it's slightly different because the momentum does not go to 0. All right, because E is greater than 0. Right? The potential energy maximum is 0. Right? So E minus V never becomes 0 if E is greater than 0. E minus V will never become equal to 0. Okay? So which means that the particle with energy greater than the potential energy comes from infinity. It comes from infinity like that. It sees more and more of the potential energy, but the momentum never becomes quite equal to 0. The momentum decreases. At the maximum of the potential energy, the momentum is a minimum, and then it goes back again. Alright, because as it travels towards the positive x direction, the potential energy decreases and it goes back like that. Okay. Similarly, you can have another curve corresponding to a higher positive energy. Alright, corresponding to a higher positive energy. So we have got this hyperbola. Similarly, we can imagine particles coming from plus infinity. Alright. You'll see that particles coming from plus infinity, it sees more and more of the potential energy. The momentum becomes a minimum at the maximum of the potential energy, and then it increases in the opposite direction. Okay. All right. So I'm just explaining this in more detail so that this idea becomes clear. Right. So for the other examples, we won't be going into so much details. So here it comes. Alright, the arrow marks are correct, am I right? Because in this quadrant, momentum is negative, so it's towards the negative x direction. Okay? So you see that this is all consistent, alright? The direction of arrows are all consistent. Okay? Similarly, for a higher energy coming from plus infinity, they are like this. Right? Now we have plotted the plots for E less than 0 and E greater than 0. There's another case, E equal to 0. There's another case called E equal to 0. Right? So this for E equal to 0, there are two cases. If you look at E equal to 0, okay, you put this is equal to 0. Right? You put this equal to 0. One solution is x equal to 0, p equal to 0. Right? As I said earlier, this is a trajectory in itself. Okay, this is a trajectory in itself. This point. All right, I'll just draw a circle here. That's a trajectory in itself. It's not a circular trajectory, this point itself, all right? The system sitting at the unstable, this is known as unstable equilibrium point or saddle point. A system, if it's at that point, it will stay there forever, all right? Unless there is some perturbation and then it falls it falls downhill almost. Okay, so that's one trajectory. Now I have a small problem here because I didn't draw it neatly. All right, now other lines corresponding to E equal to 0. E equal to 0 is p square by 2m is equal to half kx square. Right, p square by 2m is equal to half k square. So you see that p square is equal to mkx square. Right, we can take the square root. We need p as a function of x, so we see that p is equal to plus or minus square root of mkx. All right, what is this? This is of the form y equal to mx plus c. Okay, here c is 0, so these are straight lines passing through the origin. Right, these are straight lines passing through x equal to 0. These are straight lines passing through x equal to 0. So we also have straight lines here passing through x equal to 0. Right, the lines are passing through x equal to 0, but the particle is this trajectory, they don't actually reach x equal to 0, as I said before. Right, these are supposed to be straight line, but because of my sloppy drawing I cannot really draw it as a straight line here. These are straight lines, okay, like that. Sorry, these are supposed to be exactly symmetrical. Right, these are straight lines. These straight lines that never really reach x equal to, because different trajectories can not intersect. All right, like that. Okay, so we see that these are the lines corresponding to E equal to 0. They separate the two kinds of curves. All right, the curves for which the momentum. So you see that for particle with energy greater than 0, it can access all of x-axis. All right, with for particles with energy greater than 0, it can actually access all of x-axis. All right, these particles, they can go anywhere. All right, there are no classically forbidden regions for them. Okay, but these, they cannot access all of x-axis. They come here and stop and go back. They cannot access all of x-axis. So these are two different kinds of trajectories, and these are known as separatrices or separatrix. Right, these separatrixes actually separate these two kinds of trajectories. Okay, now we need to put the arrow marks. The arrow marks must be consistent, so it goes like that. Here it has to be like that. Okay, here it goes like that, and so the adjacent arrows are all pointing in the same direction. Okay, that's it. We have got the phase portrait. This is a family of hyperbola. Okay, and we have got two straight lines passing through the origin for what do you say, energy equal to 0. Yeah, so we have trajectories here for E less than 0, E greater than 0. Particles with E less than 0, there are some regions along the x-axis which are not accessible. All right, for particles with energy greater than 0, the whole of x-axis is actually accessible to the particle. All right, and the separatrices actually separate these two kinds of trajectories. So this is an example that we see in detail, and we'll go into other problems. All right, so I've got a better. I've explained these things here in some detail. You can go through it, and if you have any doubt, you can go through it again or contact me. All right. So I have given E less than 0, E greater than 0, and E equal to 0 separately. I just wanted to show how to draw it. All right. The figure looks something like this. All right. And this point, as I said earlier, did I say it's also called the equilibrium point or saddle point? All right. This point is called equilibrium point or saddle point Okay, now you try drawing this diagram and putting these arrows. You'll see that in the beginning it may be a little bit confusing, but if you do it a couple of times, it becomes really easy. Okay, and usually this kind of picture is enough. All right, when we draw for an examination, the options will be given. All right, different phase space portraits will be given. So if you are able to roughly plot it like this, you need not be really good at drawing or anything. If you are able to roughly plot it like this, then you can choose the correct answer from the options. All right, so in these exams, you also have to look at the options and take hints from the options. Okay, so for example, if the options are given, you see that the Hamiltonian is of this type, and if one of the options is not symmetric about the x-axis and p-axis, you can immediately eliminate that option. Right, because if the Hamiltonian has this form, the portrait will be symmetric about x-axis and p-axis. So you can take some hints, and maybe you will be able to eliminate some of the options without going into the full details. Okay, all right, so that's the answer to that question. The explanations I've given here. We can go through the notes. Okay, and this is the diagram. Right, this is a better diagram here. although not that much better, but this is how it is. All right, so these are the curves corresponding to E less than 0, this also corresponding to E less than 0, this is for E greater than 0, similarly here E greater than 0. As I said, particles coming from plus infinity will approach x equal to 0, its momentum will become 0 and then it will go back. All right, there are regions which are classically forbidden for these particles, whereas for these particles there are no regions which are forbidden. Right, it can access all of x-axis. It can come from plus infinity, go to the 0 of x and then go back to minus infinity. Similarly, it can come from minus infinity, go to 0 of x and then go to x equal to 0 and then go to plus infinity. All right, so the whole x-axis is accessible for particles with energy greater than 0 in this case. Okay, hope that's clear. And these are the separators. Okay, when you put the arrow marks, you have to be sure that they are all consistent. Okay, they are all in the same direction. All right. Now let's go into another problem. All right, this is one that was asked for one of the examinations. Okay, phase portrait for the potential V of x equal to x cubed by 3 plus ax squared by 2. Okay, that's a potential energy curve, potential energy versus x that's given. So this, since we have already discussed in some detail, we'll just quickly go through this. You can do this by yourself, the rest of it. Okay, the first point is to plot, the first thing to do is to plot V of x versus x. For that, the first thing is that we find the zeros of the potential energy. We see that the potential energy becomes 0 at x equal to 0 and x equal to minus 3a by 2. So we already get some idea. We note that at x equal to 0 and let's say at some minus 3a by 2, it is 0. Okay, the next point is to find the extremum points. All right, you take dv by dx equal to 0, which says that x square plus ax is equal to 0. Is that correct? Yes. All right, now you solve for this. X into x plus a is equal to 0, or x equal to 0 and x equal to minus a. So there are 2 points where it's 0. It's at x equal to 0 and, sorry, it's 2 points where it's an extremum at x equal to 0 and let's say x equal to minus a. All right, so what do we have? Let me just repeat it here. We know that it's 0 here and we know that it's 0 at minus 3a by 2. We will for extremum point. All right, minus a it's an extremum. For 0 also it's an extremum. Now we need to see what kind of extremum these are. Right, so we take the second derivative. Right, you take the second derivative, it's 2x plus a, and you check at this extremum point. The one extremum point was x equal to 0. Right, so you take 2x plus a at x equal to 0. You see that it's positive, so it's a minimum. Right, so we see that this is a minimum. This point is a minimum. There's a minimum here. All right, and similarly, you see that at x equal to minus a, which is another extremum point, all right, which I have marked here, it's a maximum. Right, it's a maximum. At x equal to minus a, this is a maximum. All right, so we know that we have got a maximum here. Okay, now what we do is, let's just check here what's our V of x cubed by 3 plus ax squared by 2. It's x cubed by 3 plus ax squared by 2. Right, now let's find the value of this potential energy at x equal to 0, at the minimum point. All right, let's find the value of the potential energy at x equal to 0. We see that it's equal to 0. So V of x is 0 at this point. We have got one more information. We already saw that this is equal to 0. But let's find V of minus a because it's a maximum. Right, V of minus a is, you see that we saw that it's a maximum. So you put minus a cubed by 3 plus a into a square, right? Yeah, a square by 2. So that's minus a cubed by 3 plus a cubed by 2. Is that correct? So what's that value? It's 6 and minus 2a cube plus 3a cube. So it's around a cube by 6. Am I right? Yeah, it's a cube by 6. So value of the potential energy is positive. It's a cube by 6 and we know that it's the maximum. So the maximum height is somewhere about a cube divided by 6. So if let's say a is 1 for example, then a cube by 6 is around 1 by 6. So that's not nice. So let's take a equal to, we just need to get the qualitative behavior, all right? If you take a equal to 3 or something, it becomes, or a equal to 2, it becomes 8 by 6. That's just above 1. Okay, so we see now we have got the details. We know that this is a minimum, so it has to increase on both directions from here. Okay, this is a minimum we said, so it has to increase in both directions, all right, and it reaches this point, and then here it hits a maximum. It hits a maximum. Did I write wrongly? This is a maximum, right? Yeah, this is a maximum, right? And then if it's a maximum, it has to decrease on both directions. It's decreasing here, fine, it has to decrease along here also. So this is our potential energy curve. This is our potential energy curve. Okay, I hope this is clear. So these details are sufficient to fix the potential energy curve, right? So I'll just go through the steps again. The first thing is that we found the points where the potential energy is 0. Okay, then we found the extremum points, and the next thing we did is that we found whether the extremum points are a maximum or minimum, and we saw that this is a minimum and this is a maximum. If this is a minimum, it means that it has to increase in both directions. If this is a maximum, it means that it has to decrease in both directions. And we also had an estimate of the value of the height of the potential energy at this point, at this maximum. At the maximum, what's the value of this height of the potential energy, by just substituting that minus a inside the potential. So what's the value of the potential energy at x equal to minus a, right? That's what we found, right? So we got the qualitative behavior of the potential energy curve. Okay, let's see. That's it. We have got the potential energy curve like that. Okay, that's exactly what we got here, right? Now we have to draw energy lines. Let's draw energy lines like this. We can have E, okay, let's say this is E1, right? This is below this. We can have E2. We can also think of particles, okay, I think with energy, let's say E less than 0. Let's imagine we can have particles with E less than 0 also. So that's possible because the potential energy is negative. Okay. All right. So that's how we have it here. So we see that if it's within this, right, within this E1 is greater than V along all these points. So this is actually allowed region. This region is actually allowed. All right, so this region is actually allowed, and it will be bound states because you will see that there will be ellipses in here, right? So you see that's exactly what we have here for E2. This is the energy line corresponding to E2. Okay, so the particle, this is an allowed region because E is greater than V, so it is just periodic motion, all right? It's just periodic motion. So it's just like the part of that harmonic oscillator potential that we talked about, this kind of a bound state. It's periodic motion, so it's going like that. That's fine. Now this is different. Okay, so we see that it's not exactly bound here, right? It's not. Let's talk about this first. Let's talk about this one first. Okay, so we drop a point here. We know that the momentum will become 0 at this point. And we see that, let's imagine a particle coming from minus infinity. Its momentum will increase. It will never become 0, all right? It will become a minimum here. It's supposed to be a minimum here. It will become a minimum at this point, right? This is the point where the momentum is minimum, all right? And then again it increases, and then it encounters this point. The momentum again decreases, all right? Because the potential energy first decreases and then increases. So the momentum becomes 0 at this point and then turns back, and we have got these trajectories. Okay. Now we can think of particles with energy E2 again. We can think of particles with energy E2 which are outside, all right, coming from minus infinity, and you will see that it comes from plus infinity, and you see that it has a classically forbidden region and it goes back, right? Because at this point the particle coming from minus infinity, it will come, the momentum will decrease, and then it will go back, all right? Because if you see that if energy is E2, inside this, right, for example, the height of the potential energy, okay, this is the height of the potential energy, this is the height of the energy, you see that V is greater than E or E is less than. So this is classically forbidden. This region is classically forbidden, all right? Similarly, for particles of slightly greater energy, we have got hyperbola here. So we have got all sorts of things here. Now what about particles with exactly energy E, this energy E? What about these particles, all right? These particles, we see that all right, they will come from infinity. Yes, it reaches here, and then, okay, there are trajectories like that. These are separatrices in this case. Right, because it actually separates two kinds of motion. You have got a bound state, a periodic motion here, and a particle coming from minus infinity and going to plus infinity. Right, so these are separatrices. Okay. Now, just by drawing the potential energy curve and drawing the energy lines, it's easy to plot these things. So we see that particle coming from plus infinity also is possible, but you see that all the regions are classically forbidden. All right, there can be particles coming from plus infinity, but all these regions are classically forbidden because this energy is less than the potential energy. Okay, E is less than V. So this region is classically forbidden. So we don't have any hyperbola here. Okay, I hope this is clear. The next problem is the phase portrait for a simple pendulum. Right, it's a very familiar system. Let's look at how the phase portrait are. All right, so the potential energy curve is like this. The potential energy as a function of x is given by this thing. All right, it's 1 minus cos x, so you can write a sine square x by 2, which means that it's positive everywhere because it's sine square. All right, now we plot, first thing is to plot v of x as a function of x. All right, you know the plot for sine. Okay, we don't have to really do the plotting thing. Right, the phase trajectories are then sketched for energies E1, E2 and E3. Right? That's what we do. Okay, we have got different energies E1, E2 and E3. Okay. And this is the sine square x curve. All right, that's not particularly complicated. We all know how to plot a sine square curve. All right, so we see that this is the potential energy curve. Right, let's see how the diagram looks. Right, first let's look at energy E1. Let's look at energy E1. All right, immediately we see that there are regions which are classically forbidden. For example, this region here, E is less than V. So this region is classically forbidden for E1. Similarly, this region is also classically forbidden for E1. Right? But if it is between these 2 points, what happens is that it has a periodic motion because it just looks like the harmonic oscillator potential in this point. Okay, so we've got this periodic motion. It just looks like the simple harmonic oscillator potential. Of course, it's also a simple harmonic oscillator for small oscillations. All right, so that's what we have got here. Okay. All right, now what happens for this is the case E1, E2. Let's leave E2 for a moment. Let's look at E3. Okay, so here E3 we see that everywhere along the x-axis E is greater than V. Right, all along the x-axis the energy is total energy is greater than the potential energy. So the momentum never becomes 0. It's square root of 2mE minus V. Okay, so the momentum never becomes equal to 0. Right, it decreases, of course. So it comes from here, for example, if it's coming from minus infinity, you see that here we are talking about this angles. All right, so this we see that the potential energy decreases. The momentum decreases as as it sees more and more of the potential energy. It decreases, but it never reaches a 0. Right, it goes like that, like that, like that. All right, now this trajectory corresponds to the case of rotation. All right, if you give it enough energy, if you give the simple pendulum enough energy, it just starts rotating. All right, now this curve corresponds to a rotating simple pendulum. If it has enough energy, it just starts rotating. Okay, that's what happens. All right, what we have here in between is a separatrix. Right, this is the case where the momentum becomes 0 at one point. This is the case where the momentum becomes 0 at one point. All right, so you see that the momentum becomes 0 as you increase x. All right, if in this case x stands for theta. So if you increase theta at one point, if it has just enough energy, at one point the momentum becomes equal to 0. If it has just the correct energy, the momentum becomes equal to 0. All right, now this is a point of unstable equilibrium. Right, now these trajectories don't really intersect, but this itself is a point of unstable equilibrium. It remains, if it is there, it remains there forever. Okay, that's what happens. But now if there is a small perturbation, it could either go towards positive x direction or towards minus x direction. So if a pendulum is standing like that, okay, that corresponds to this point. Okay, so if you give just enough energy, it can come and stand here like that. Right, if you give exactly the correct energy, so it reaches a point of unstable equilibrium, but it could either fall towards minus x or towards plus x. All right, this is falling towards minus x, and this is falling towards this is falling towards minus x, and this is falling towards plus x. All right, and this is separatrix. Right? Because the separatrix actually separates between two kinds of trajectories. One corresponding to periodic motion and the other one corresponding to unbound or rotation in real space. All right. So we see that rotation in real space, actually rotation in real space corresponds to an open curve, whereas a periodic motion in real space corresponds to a closed curve here. Right. So in real space, it just is the opposite. All right. In this case, in the real space, periodic motion. Okay, in the real space, periodic motion just goes like this, but the rotation gives you a closed curve. Okay, rotation gives you a closed curve. Right. In this case, it's just the opposite. The rotation of the simple pendulum gives you this open curve in phase space. Right. So this is not very difficult. We just plotted the potential energy. We plotted the different energies. We drew different lines corresponding to the different values of energy, and we saw the different cases. All right. Okay. Now to the next problem. This problem was asked for one of the previous NET exams. You see how easily we can solve this problem. The bob of a simple pendulum which undergoes small oscillations is immersed in water. It's immersed in water. So what happens if a simple pendulum is immersed in water? All right. We know that even if it starts oscillating, the energy gets quickly dissipated, and then the amplitude of the oscillation will decrease, and it will approach the rest position. All right. Now, which of the following figures best represents the phase space diagram for the pendulum? That's the question. Right. Now we know that for a simple pendulum, for small oscillations, it's just like a simple harmonic oscillator. We have already seen it in the previous problem. Right. Now these ellipses corresponds to definite energies. Right. So, but what happens with the case where there's dissipation? When there's a dissipative force acting, the amplitude decreases, or the energy, the total energy decreases. Am I right? So when the total energy decreases, what happens is that even though the pendulum starts on this surface, it slowly loses energy and it goes to another surface of a lower energy, and then like that goes on and approaches the point x equal to 0, p equal to 0. That's what will happen. Okay. So we know that it's either this or this. Which one is it? Right? Now if you look at this plot, you see that, and if you put the arrow mark, you see that as x increases, the momentum increasing in this direction. So it can start here. So if you look at this arrow marks, all right, you see that what happens in this case is, we can put arrow marks here. What happens in this case is that, all right, it seems to get some energy from outside. All right, it seems to get some energy from outside. It starts with a lower energy. Okay, you can imagine an ellipse. It starts with a lower energy, but then goes on into higher energy surfaces. So it's getting energy. This is gaining energy. All right. So this could be something like what do you say, forced pendulum or a driven pendulum. This could be a driven pendulum, but we are asked a pendulum which is dissipating. So in that case, we see that it should trace curves of lower and lower energy. So this is the case. All right. You have to be careful. These look very similar, but they are different. All right. They are different. You should be able to see the difference, because it starts with the higher energy and then goes and it approaches the point x equal to 0, p equal to 0. So this is the correct answer. Now this could be the correct answer if it does not lose energy. Right? If it does not lose energy, this could be a possible case. All right. It's not this. This is the correct answer for a simple pendulum which undergoes small oscillations. Then it's simply the simple harmonic oscillator, and it's immersed in water. All right. So you get 5 marks. That was the 5-mark questions. You get a 5 mark without much difficulty. But as the year goes, all right, the problems may get a little bit more complicated. You may have to draw a potential energy curve and then actually plot the phase space portrait, just as we said. All right. Okay. Right. Which of the following set of phase space trajectories is not possible for a particle obeying Hamilton's equations of motion? All right. These are the options which is not possible. This also was a previous year NET question. I just took it directly out of the question paper. All right. So we see that for one, okay, we see that for this case, these are intersecting. All right. The different trajectories are intersecting. So at this point, it's not clear which way the evolution is. All right. There's no unique evolution in this case. So this is not just possible. Okay. In these cases, we are talking only about autonomous systems where we don't change the rules of the games in between. So we don't change the rules of the game in between. All right. You start with the Hamiltonian and you don't give any extra energy, or you don't change the Hamiltonian. In that case, that's the case that we are talking about. If there is a case where these trajectories intersect, then we should get rid of it. Okay, so this is the one. It's not possible. This kind of a phase-space trajectory is not possible for any conservative or autonomous system. Okay, it's generally autonomous system. Different phase trajectories cannot intersect. Right? The next one, the trajectory on the z-pz plane of a ball bouncing perfectly elastically off a hard surface at z equal to 0. Okay, that's not difficult. Alright, we see that here we have got the trajectory of z-pz plane of a ball bouncing perfectly elastically off a hard surface at z equal to 0. This means that we have got a hard surface. In the real space we have got a hard surface, alright, at z equal to 0. This means that for z negative this is not accessible. Right? For z negative this is not accessible. Right? So we look at these diagrams, and from the question we see that there's nothing corresponding to z less than 0. Alright, it's a hard surface at z equal to 0. So z less than 0 is not accessible. So immediately we can neglect, so we can remove these two options from our possibilities. Alright, why? Because here there's z less than 0, here also there is something corresponding to z less than 0, but we are talking about a system which has no access to z less than 0 for negative values of z. Alright, now which is the answer? Now we can just imagine what happens to a ball when it bounces. Right? We know that when it bounces off the floor, its momentum, so first it has a maximum momentum and then it decreases as it goes up, and then it comes to a stop when it goes to a sufficient height. Alright, and then it comes back, and then the momentum increases in the opposite direction. That's what's happening in real space. Alright, so which of these two diagrams correspond to this thing? Right? So if you look at this, we see that the momentum starts and the momentum decreases as z increases. See, we need the case where the momentum decreases where the z increases. Right? Momentum decreases when z increases. That's the case we are talking about. So here we see that the momentum actually decreases as z increases, comes to 0 at some value of z, and then the momentum increases in the opposite direction. Okay, that's exactly the case we have. Right? And what happens? There's no dissipation, and then next the ball starts again here. Alright, if there's no dissipation, the ball again starts from here and traces this curve all over again. Alright, for a lower energy, if the ball starts with a lower energy, it would correspond to a curve like this. Alright, okay. So this is not this. In this case, we see that the momentum is increasing as z increases. Alright, the momentum is increasing as z increases. So this cannot be the case. So the correct option is option A. Right. Now these two the next two problems are left as exercises for you. Right. So we are given a potential. These two questions were asked for previous NET exams. We see that the questions can get complicated. Right. It could be a simple case of a dissipated pendulum, or right, a pendulum with dissipation, or in this case a bouncing ball. These two are simple, but now they have asked something slightly more involved. Right. You really have to do this. Okay. So how would you do this? You first plot the potential. First plot the potential energy curve, potential energy versus x, alright. Draw the energy lines. You remember the steps for plotting the potential. If not, you can go back and check. Alright, we did it for one case. And then you draw the energy lines and you just draw the phase space diagrams corresponding to this. Alright, sometimes just by looking at the potential energy curve, you will be able to pick out the correct answer. Alright, you will see that some of them can be neglected straight away. Okay, that can be done. So please try that. All right. So I ask you to take hint also from the options. All right. When you see a few options in your examination, take some hint from the options. Look at the options and look at the potential energy curve and see which one is more plausible. All right. Which one is possible, and then maybe you'll be able to eliminate something and you'll save some time. Okay. All right. So you try that. I've given the solution in the end of the. At the end of the slides, you can check that, but you should really try this. All right. Now, if I am wrong with my solutions, you please inform me. Okay. At least the solution can be seen as a case for some potential energy function. Right. The next problem is the potential energy is minus k square x raised to 4 plus omega square x square. Okay, again, plot this potential roughly, qualitatively, and from the shape of the potential energy curve, you will see what kind of phase-based trajectory is possible. All right. Now, I think the solutions are this. Okay, for exercise 2, it's this. For exercise 3, it's this. All right. So you see that they are similar. The shape looks rather similar, kind of. Okay. Now, I think this is the answer. If I am wrong, you can just correct me. Anyway, you can take this as an example where if the potential energy curve is given like this, all right, in some questions, they may give you the potential energy curve directly, right, and you just have to obtain the phase space portrait, right. So, in this case, we see that suppose the potential energy curve has this form, you see that the phase space portrait will be of this form. There are bound states corresponding to this, all right, corresponding to this, and there are separators corresponding to this energy, all right, and there are again bound states in the case of periodic motion corresponding to between these 2 points also, all right. Let's say x1 and x2. There are 2 kinds of periodic motion. One periodic motion is between these 2 points, okay, and the other periodic motion is between these points. There are 2 kinds of periodic motion, and you can do this. Okay. Now suppose the potential energy curve is of this form. We see that there is periodic motion here, there is separatrix corresponding to this, okay, and for greater energy, okay, you can draw an energy line here. For greater energy you get something like that, okay, because the momentum will become maximum when the potential is minimum, and it goes like that. All right, you can go through these examples. All right, now I hope you can get an easy 5 marks in your classical mechanics competitive examination, net JRF examination, if you are if you get a little bit practice with this. All right, this is not a difficult thing. This is an easy 5 marks for you, right? So with that, I'll conclude this session. Thank you.